Another metric that we can use for characterizing a system's noise performance is something called the noise figure. And so our noise figure, expressed in decibels, F sub dB, is equal to 10 times log base 10, and then in the argument for our log, in the numerator we have our signal in divided by our noise in, and in the denominator we have our signal out divided by our noise out. So essentially we're characterizing how much our signal to noise ratio has changed. We'll also need to specify a temperature. So typically that'll be 290K because that's roughly room temperature. And so what this T out is doing is this indicates our input temperature of some source to the amplifier. So indicates the effective the effective noise temperature to be more specific. So effective noise temp of source connected to our amplifier or to our system. So let me just say to our system to keep it more general. And so what that means then is that our noise in can be characterized by K sub B, our Boltzmann constant, times our bandwidth, times that temperature T naught. And all of those signal in, signal out, noise in, noise out. So S in, our noise in, our signal out, and our noise out are all going to be powers expressed in watts. And so they don't necessarily all have to be watts so long as you're using the same units for all of them, because again, we're sort of comparing our signal to noise ratio coming into the system to our signal to noise ratio coming out of the system. So sort of to get an idea of one of the endpoints, let's consider our sort of ideal case, which would be a noiseless amplifier. So if we have a noiseless amplifier, we would be expecting it to not have any change on our signal to noise ratio, such that our signal in over our noise in is equal to our signal out over our noise out. So it's amplifying both the signal and the noise, but it's doing so equally such that the ratio stays the same. And plugging into this equation up here, we would see that our argument of our log would just be 1. And so log of 1 is 0. So what this means is that the noise figure for an ideal noiseless amplifier would just be 0 dB. And so as that gets larger, that indicates we're getting further away from that ideal case. We can also relate this noise figure to our previous discussion of effective input temperature. So let me come back here, not FB, F sub dB, our noise figure in decibels, and our effective input temperature of an amplifier, or more generally, the effective input temperature of some system. They're both conveying the same information. So we actually have a way that we can sort of go back and forth between the two. So we can say that our noise figure in dB at some temperature, effective input temperature, is equal to 10 times the log base 10 of our effective input temperature divided by 290 Kelvin plus 1. And so of course we could rearrange that as well if we had our noise figure and we wanted to find the relevant effective input temperature. And again, to be more general, we could maybe change this for T system. And then if our system is just one amplifier, of course that would just be T sub E. One other thing to note is that so far we've been talking about a noise figure. In some cases you might see something called a noise factor. And so what this is just an earlier definition that was used, and the noise factor was just defined as F is equal to our signal in over noise in divided by signal out over noise out. And so over time, it became more convenient to use our noise figure. So basically putting this into decibels. But in some cases, you might still see that noise factor, so I just want you to be familiar with that as well.